Welcome back to the second part of electrostatics. In this session, we are going to discuss about electric field produced by a point charge and its properties, electric field lines and the properties of electric field lines, electric dipole, the dipole moment, the torque acting on a dipole placed on an electric field, etc. Now we are going to see what is electric field. It is a region around a charge or group of charges where its influence is experienced. Such a region we call it to be the electric field. Now we are going to define what is electric field. To find the electric field at a point, we place a test charge at that point. Find the force experienced by the test charge. We divide that force by the magnitude of the test charge. Then we will get the strength of the electric field at that point. Therefore, the electric field strength is defined in this way. An electric field at a point is defined as the electrostatic force per unit test charge acting on a positive test charge placed at that point. The electric field is a vector quantity. Mathematically, it is denoted as E equals F by Q0. That is, the direction of the electric field is acting along the direction of the force experienced by the test charge. Now we are going to calculate the electric field due to a point charge. Consider a point charge Q placed at a point 1. We determine the electric field at a point P at a distance r from it. To find the electric field at P, we place a test charge Q0 at that point. By Coulomb's law, we can find the force between the charge Q and the test charge Q0. We know the Coulomb's law. F equals K into Q0 divided by R square. But we know E equals F divided by Q0. Therefore, you divide the force by Q0. Then you get E is equal to KQ divided by R square. You know the value of K. It is 1 by 4 pi epsilon 0 epsilon r. Therefore, we can write the equation as E equals 1 by 4 pi epsilon 0 epsilon r into Q divided by R square.
It is clear that electric field E inversely proportional to R square. This is a radial field which looks same in all directions when seen from a point charge.
In this way, we can represent the electric field around a point charge. Electric field lines is a pictorial representation of an electric field. They are imaginary curves, straight or curved, along which a free positive charge would move if it is free to do so. Now we are going to discuss various properties of electric field lines. Number 1, they start from positive charge and end in the negative charge. If there is only one charge, lines may start or end at infinity. Number 2, the tangent to the line of force at any point gives the direction of the electric field at that point. Number 3, concentration of the lines shows the strength of the electric field. Number 4, in a uniform electric field, they are parallel and equally spaced. Number 5, they never intersect. They do not form any closed loop. This is due to conservative nature of electric field. Now we see what is electric dipole. Two equal and opposite charges separated by a very small distance form an electric dipole. What is dipole moment? It is the product of one of the two charges and the distance between them. It is a vector quantity and its direction is from negative charge to positive charge along the axis of the dipole, and the unit is coulomb meter. So we can write it as the dipole moment P equals Q into 2A, where 2A is the length of the dipole. Now we are going to see what is the torque acting on an electric dipole when placed in a uniform electric field. Consider a dipole AB of dipole moment P placed in a uniform electric field of strength E at an angle theta with the direction of the electric field. The force acting on the plus Q charge is plus EQ. This is in the direction of the electric field. Again, the force acting on the minus Q charge is minus EQ. This is opposite to the direction of electric field. Hence, no net force is acting on the dipole. That is, the net force acting on the dipole is 0. Two equal and opposite forces separated by a distance constitute a couple. Therefore, torque is equal to force into perpendicular distance between the two forces. That is, torque is equal to QE into 2A sin theta. That is, tau equals PE sin theta. In vector form, we can write it as tau equals P cross E. The torque tries to align the dipole along the direction of the field. Special cases of torque. When theta equals 0, that is, when the dipole is placed parallel to the direction of the electric field, then torque tau equals 0. This is in stable equilibrium. Again, if theta equals pi by 2, that is, the dipole is placed perpendicular to the direction of the field, then torque tau equals PE. This is the maximum torque acting on the dipole. Again, when theta equals pi, that is, the dipole is placed opposite to the direction of the field, then torque is equal to 0. This is the case of unstable equilibrium. We are going to find the electric field at an axial point of a dipole. AB is an electric dipole of two charges, minus Q and plus Q, separated by a small distance 2A. P is a point on the axial line of the dipole at a distance r from the midpoint O of the dipole. The electric field at P due to the charge minus Q is even equals 1 by 4 pi epsilon 0 into Q divided by R plus A the whole square. Its direction is along PA. Again, the electric field at P due to plus Q charge E2 equals 1 by 4 pi epsilon 0 into Q divided by R minus A the whole square. It is along BP. Therefore, the magnitude of the resultant field E is given by E2 minus E1 and its direction is along BP. Therefore, E equals E2 minus E1, 1 by 4 pi epsilon 0 into Q divided by R minus A the whole squared minus 1 by 4 pi epsilon 0 into Q divided by R plus A the whole square. Again, we can take Q by 4 pi epsilon 0 as common. That is, Q by 4 pi epsilon 0 into 1 by R minus A the whole squared minus 1 by R plus A the whole square. Again, Q by 4 pi epsilon 0 into, in the numerator, R plus A the whole squared minus R minus A the whole squared divided by R squared minus A squared the whole square. On simplification, we get Q by 4 pi epsilon 0 into 4AR divided by R squared minus A squared the whole square. Therefore, 1 by 4 pi epsilon 0 into 2PR divided by R squared minus A squared the whole square. Here, P equals Q into 2A is the dipole moment of the dipole. For a short dipole, A very much less than R, then A can be neglected in the denominator. Now the equation becomes E equal 1 by 4 pi epsilon 0 into 2pr divided by r raised to 4. Again, on simplification we get E equal 1 by 4 pi epsilon 0 into 2p divided by r cube. This is acting along BP. Now we are going to see the electric field at an equatorial point of the dipole. Here, AB is an electric dipole of two charges, minus q and plus q, separated by a small distance 2m. P is a point on the equatorial line of the dipole at a distance r from the midpoint O of the dipole. Here, electric field at P due to plus q charge E equal 1 by 4 pi epsilon 0 into q divided by r squared plus a squared. Electric field at P due to minus q charge is E equal 1 by 4 pi epsilon 0 into q divided by r squared plus a squared. The components of the fields due to plus q and minus q charge normal to the dipole axis is E sin theta, and that will cancel out, and the components parallel to the dipole axis is E cos theta, and it will add up. Therefore, the resultant electric field is E equals 2E cos theta. The resultant electric field E equals 2 times 1 by 4 pi epsilon 0 into q divided by r squared plus a squared into a divided by root of a squared plus r squared. Here cos theta equals a by root of a squared plus r squared. On simplification we get E equal 1 by 4 pi epsilon 0 into p divided by r squared plus a squared the whole raised to 3 by. For a short dipole, a very much less than r. Therefore, we can write it as E equal 1 by 4 pi epsilon 0 into p by r cube.
The direction of the electric field at any point on the axial line will be parallel to the dipole moment. The direction of the electric field at any point on the equatorial line will be anti-parallel to the dipole moment.
Now we are going to compare the strength of the field along the axial line and along the equatorial line for a short dipole. E axial is equal to 1 by 4 pi epsilon 0 into 2p by r cube, and E equatorial line is equal to 1 by 4 pi epsilon 0 into p by r cube. On comparing the above two equations, we get E axial is equal to 2 times the field along the equatorial line.